So the first lecture is going to be introduction about neutrinos. And the way that I prepare this lecture is using my personal bias. So I'm someone who may call a listening learner. So I like to listen to stories and put attention on those stories, and then just listen and think through what I'm listening. And then once I have finished listening, either a postcard or something like that, the way that I do is like, okay, I really find this. I have questions about this. I didn't understand this topic, so then I go back to take a book or doing research on my own and say, okay, I'm filling my gaps, but I just want to listen to the story. And sometimes I didn't like the story, and it's okay, I didn't like this topic, so I move on. So as opposed to go to a formal lecture where I play some complex concepts and abstract concepts and follow with some formulas and some mathematical rigors, I want to tell you a story about neutrinos, right? And also the reason that I prepared this is that I don't know if all of you have taken quantum mechanics or maybe introduction to particle physics courses and all of that. So we have a mixed audience. So I just want to tell you for now, and this is the way that I prepare this, telling the story about neutrinos. At the end of the week, you can tell me you should completely try a new approach because that didn't work at all. So I couldn't follow you or something like that. So please tell me what do you think about the way that I prepared this, even at the coffee breaks or at the end of the week. So yeah, so I'm going to talk about neutrinos. It's not working anymore. Always something. Yeah, so I'm going to give you the history of neutrinos, what we call the neutrino puzzles and neutrino oscillations. And again, since this is going to be a story about neutrinos, let's start once upon a time in the 1930s. Physics was in one of the most proliferal years. By this time, quantum mechanics was already born. Everyone is talking about modern physics. People doing a lot of experiments. People were discovering new particles and all of that. So everything was excited, and everything was like, oh, this is great. We are doing new physics. We are learning about the fundamental parts of the atom. And by these years, everything was well understood in terms of conservation laws. So energy must be conserved. Linear momentum must be conserved. By this time, also spin was already known, so spin must be conserved. So everything should be conserved, and these are the fundamental pillars of the new modern physics. Not only the classic physics, but also the modern physics that we are observing. That was pretty much the same when people were looking into alpha decays. They have discrete energies, and they were well understood at that time. They say, okay, these alpha particles is just one state or other state because of the quantization. Gamma decays also were interpreted as photons with a well-defined energies. So everything was making sense. Just to give you some context, this is a photo of Rice University in 1932. So you can see how things have changed since then. And yeah, so people continue doing experiments and more observations about particle physics, nuclear physics, and one of those experiments that we're looking is something called beta decay. But there was an issue with the beta decay. So when scientists were observing the beta decay, they should expect a line for the electron energy. So in a beta decay, you have some material that goes into this beta decay, and it produces a beta particle, which is an electron. And so you say, okay, you can measure the energy of the electron. I know what was my parent particle. I know what is the daughter element in the electron. So there is nothing to worry about. I just have to basically subtract the energies of the parent and the daughter, and I should estimate what should be the energy of the electron. And so it's always the same parent particle and the same daughter particle or nuclei. There should be just one line, right? Always have to be the same value. Always have to be the same value. But it wasn't the case. They observed a continuous spectrum. So if I can give you just an analogy of what will be beta decay, using some of the terminology that we know now, is, for instance, if you take an element, let's say boron 12, so boron has 12 nucleons. It has 5 protons and 7 neutrons now. We know that fermions can occupy one state of energy. They cannot be more than 2. For instance, again, remember, by this time they know about spin, so in principle, you can have the same 2 number of neutrons in the same state, energy state, but just one different spin orientation, and you still obey Pauli exclusive principle, right? So, but then what is happening is that since this neutron cannot go into the same state, it has to somehow transfer into a proton, and it can go in this energy state, right? So in principle, people think that, oh, the beta decay is just basically the transition of a neutron into a proton, and in this case, since you now have 6 protons, it becomes carbon. And you have the electron, which is just to conserve the energy. And again, since they say we always have to have always boron, and always going to be carbon 12, so we in principle can measure and estimate precisely what should be the energy of this electron. Does that make sense? There's nothing, there is no black box here, right? However, when they're doing the measurements, they see a distribution over the energy of the electron, as opposed to the expected value. So in some cases, the energy of the electron was here, which means that it was missing all of this energy. Or sometimes it was here, it was missing all of this energy. Sometimes it was here, it was missing some little energy. So there was something wrong, right? Because say, oh, I know what is a boron 12, I know what is carbon 12, I know how much energy there is there, and I can measure this, but somehow I'm missing the energy. What's going on? So, okay, they say, well, maybe energy is not conserved at all, right? So say, okay, what else can be wrong? So linear momentum also is something pretty easily. We can do from physics 101. If you have a body at rest and there is a decay, you should know that the daughter particles should be back to back or in opposite direction, right? Just because of conservation of linear momentum. When they're looking at the direction of the electron and the recall, also they found that linear momentum wasn't conserved. So, okay, what else cannot be conserved? At that time, also, they knew about the spin, and they knew that the proton and the electron has a spin of half. So they say, how can something will produce 2 particles with a spin 1.5? So it seems like also angular momentum or spin is not conserved. So this was really a crisis in the modern particle physics, because some of the fundamental pairs of physics wasn't conserved, or we didn't understand what was happening. Energy is not conserved, linear momentum is not conserved, and angular momentum is not conserved. So you can see how, at this time, physicists were like scratching their heads, like, what's going on? We come out with a modern physics, we're supposed to be understanding this, we have all of these experiments, radioactive experiments from gamma rays, alpha decays, we understood pretty well those lines, and then when we're looking into the beta decay, we find out that nothing that we know works. So one of the founders of the modern physics, Niels Bohr, at some point, I guess he just said that it's not out of the question that maybe energy is not conserved in beta decay. So maybe this is an anomaly in physics, and that's what we have to live with. But again, people are more curious and say, maybe there is a solution to this problem. And this is where a physicist named Pauli came out with a brilliant idea. He came out with this idea just by writing a letter on December 4th. The letter is written in German. You can find a copy of the letter and the translation online. And just to give you highlights about this letter, and the letter starts with, dear radioactive ladies and gentlemen, he sent these letters to the people who were attending a conference in Germany. And he said he was aware of these issues of the beta decay, that there seems to be some missing energy. And he says that I have hit upon a desperate remedy to save the law of conservation of energy. So he says there could be existing electrical neutral particles, which I will call neutrons. Again, remember, by this time the neutron wasn't discovered yet, in the nuclei. So it should have a spin 1.5. So he was checking all the marks that were not conserved, basically, right? So like, you can say, oh, it was brilliant, or it was a pretty much long-hanging fruit there, right? So we don't conserve energy, so there is something else. We don't conserve spin, okay, it should be a spin and a half, and it should be small mass and carry the missing energy from the beta decay. However, he was like, maybe I'm a little bit crazy, and says, I don't want to publish anything about this, and I just want to run this idea through you, through this letter, basically. Because how likely will be that we should detect this neutron in an experiment? And he said that I admit my remedy may seem almost improbable, because one probably will have seen those neutrons if they exist for a long time. So say, yeah, if they are there, we should see them, right? We are able to see the electrons, we are able to see gamma rays, we are able to see alpha particles, beta particles. So why we couldn't see this neutron if they exist, right? So we're like, maybe there is something special about this. At the end of the letter, one of the most astonishing statements that I would say in physics is he says, I cannot be there. Sometime indispensable here in Zurich because of a valve of the 9 of December 6 to the 7. So he said, he threw an idea about solving one of the most fundamental physics problems, and he decides to miss the conference because he wants to go to a party. So I dare you to do the same with your advisors at some point in your career. And say, if Pauli can do it, why can I not do it, right? And yeah, so that's a fun aspect about this famous letter. So he checked all the marks. Should be electrical neutral, spin and a half, small mass, smaller than the electron, and carry the missing energy. 2 years later, there was an experiment in the UK by James Chadwick, where they basically were bombarding beryllium with alpha particles. And what they observed in the results is that they have a particle very similar to the proton with no electric charge. So then they say, oh, this is the neutron. We will call this neutron. And that's what the neutron was discovered. And again, it's just similar mass to the proton, pretty much the same mass, but no electric charge. And therefore, this is the neutron. And then, therefore, this is not the particle that Pauli was postulating, because the mass is relatively large compared to what we're expecting in the beta decay, because it's pretty much the same mass as the proton. It was neutral, but the mass wasn't completely different. And then Fermi, Italian physicist, was also interested in this process, the beta decay. And he said, okay, we know that this neutron that Pauli was telling is not the neutron that Chadwick discovered, so it's still a neutral particle, but small, so we call it neutrino, which is little neutron in Italian. And he said, instead of a neutron transitioning into a proton, I will think about this interaction as a 4-interaction particle. So my neutrino, my little neutron particle, will interact with the neutron in the nuclei and produce a proton and an electron. And he said that the energy density, the energy distributions of this process should be proportional to the energy square, where this difference is the energy missing. Q is the energy, the maximum energy available in the reaction, and energy is the energy of the electron. The difference should be the energy of the missing particle. So yeah, okay. So yes, we follow Pauli's recipe. We have a new particle. It's small, 1.5 spin, small mass, and I can feed the data, and the energy distribution fits this formula. So my interaction is telling me that this should be the energy of the missing particle. So by that time, they say, okay, now how often these particles will interact with matter so that we can detect them, right? Because remember, we say if this particle exists, somehow we should be able to detect them, right? We have to see them. Back in those days, people were postulating particles, and they were observing those particles. And every time that they see something in the lab, say, okay, this explains this and all of that. So following that criteria, say we should see if we can detect this neutrino somehow. But when they calculate how often they will interact with matter, basically they have the question, if I have a neutrino and it travels to matter, when it will neutrino interact? That's known as the mean free path, right? And I say, what is something dense that will allow us to interact neutrinos promptly and quickly? Okay, lead. And when Fermi calculate what will be the mean free path of a neutrino from beta decay, which is around MeV, it was significantly enlarged. So if you translate that into light years, it's more than 100 light years. So the neutrinos rarely interact. And at this point, back in those days, in the 1930s, people say it's impractical to detect neutrinos. And when Pauli found about this, he said, oh, I have done something terrible. I postulate a particle that never is going to be detected. So this is such a big mistake in my career, right? Because, yeah, it is impractical, right? How are you going to have this many kilometers of lead to detect one neutrino? And then, so the question is, the neutrinos can be ever detected at all, right? If they really interact, you need to have a lot of mass. And so how you can do that? So now, just one side note, I show you a picture of Enrico Fermi. This picture was taken in 1950 at the University of Chicago. In 1938, Enrico Fermi was awarded the Nobel Prize for something about relative decays. And I guess at some point, because now he was already famous, someone said, oh, we are going to do some photoshopping about you, so please write something in the board so you look smart and interesting. Try to work in some complex things that no one will understand, but since you are a Nobel Award winner, people will say, okay, who cares, right? So I don't know, this is what I know. I don't know if he wrote these equations or someone else, but he was posting in that blackboard. And there is something that is called the fine structure constant in physics, or the alpha constant. This basically tells you the strength of how electric particles interact with electromagnetic force. And you may know that physicists tend to have many unit systems, right? You can choose when you are working in EM, you can choose many different unit systems, and it's, oh, it's just because you have a different result just because I'm using a different unit system. And it happens that regardless of the unit system that you're using, this is wrong. So the alpha constant is this. So I don't know if he didn't notice or someone else wrote that equation. But you can see that even Nobel Prize winners make mistakes. So yeah, there's just a sad note about this picture. This is a famous picture. And you go Google, this is one of the first images that will appear, and it has a big mistake there. Okay, so then what is the conceptual wave to detection for neutrinos? So Pauli says there should be a new particle in the beta decay. Fermi says, yes, I can give you the theory about this particle. It will rarely interact with matter. We know how the energy should look like. But in principle, if that particle exists, you should be able to do the inverse process, the inverse beta decay process. Meaning that if the neutrino exits the nuclei, can interact with a proton from another nucleus and hit a neutron and produce a positron, right? So now, the question is, where do we get the neutrinos and where we get the protons, right? So now we move into the 50s. By that time, between the 40s and 50s, you may know that within the US there was a significant program to work on nuclear weapons. And one of the physicists that was leading those weapons was Frederick Reines. And his colleagues were aware of the great number of neutrinos produced in a fission process. The fission process is basically what triggers a nuclear bomb, right? The fission process is when you have a heavy element that get into lighter elements, and this is a chain process, and it releases a significant amount of energy. The neutrinos are not produced in the fission process. They are produced with the products of the fission process. So when you have this heavy element decay into lighter elements, those lighter elements are neutron-rich. Because they are neutron-rich, they will decay into beta decay and become stable. That's how you produce the neutrinos, not just because fission process. It's just the products of the fission process will go on their beta decay. And on average, for every beta decay, you produce 6 neutrinos. So you say, oh, there is a lot of neutrinos in a nuclear bomb, basically. So in principle, he said, I'm tired of tested nuclear bombs in the Pacific, so I want to do some fundamental physics. I want to measure this neutrino. So what if I throw another bomb just to study neutrinos? And the idea was the following. These guys were working in Los Alamos National Lab. I guess everyone is familiar with that if you have seen the Oppenheimer movie. And there is publications about the first idea that they have. They come out with, first of all, we have to find a detector that will allow you to detect neutrinos, to detect the signals of this interaction, right? So we know that the neutrinos will exit and they will hit a proton from our materials in the detector, and they should produce a neutron and a positron. So the idea is that we should make a detector so that we can collect these signals. And if we collect these signals, that means that there is a neutrino interaction, right? So one of the first ideas is that we have to develop a detector. And they started to develop this giant liquid scintillation detector. And this is a publication from Los Alamos, and this is a sketch of one of the first designs. And if you zoom, you can see that for whatever reason, they happen to name this sketch as the El Monstruo, which is monster in Spanish, for whatever reason. And then say, yeah, we know that nuclear bombs have a lot of neutrinos, so what if we blow up some nuclear bomb? Well, of course, there's going to be a fireball, and we don't want to destroy our detector. So we have to somehow put our detector in a safe way so that it will collect the signal, we can read out the detector, and we still have the explosion, and we measure the neutrinos, but with a safe detector. So the design, and again, this is a technical document from Los Alamos, includes some feathers and foam, so that you put the detector here, somehow the detector will be in free fall, you have the explosion, and then neutrinos will interact, and your detector will save because of feather and foam. And again, you can Google this, these are technical documents. And the project was approved by the director of Los Alamos. For whatever reason, it didn't happen. So what they say is like, okay, what if we, instead of using a nuclear bomb, we use something similar? So a nuclear reactor is pretty much the same thing, but with a controlled fission process, right? As opposed to a nuclear bomb, you can have a reactor when you control the fission process and you know how much energy you're releasing, how many neutrinos you have, and all of this is with a control, in a controlled environment without the fireball, right? So in 1953, they started doing these attempts in a reactor, and they didn't find conclusive evidence about this. And what they found is that they seem to get some signals, but they weren't aware whether it was background, some accidentals, or something else. And one of the things that they found is that they have to shield the detector with a lot of material to avoid contamination from outside. In this case, it's called, for instance, neutrons from the reactor, or even cosmic rays from just the environment, right? So cosmic ray, we are bombarded for cosmic rays. Those are particles that coming out of space, interact with the atmosphere, produce some particles, and those particles travel through the air, through our offices, to every building, and you will see them in your detector. So they come out with a design of a sandwich detector when say they place a lot of shielding. They have this liquid scintillation, and they have something called photomultipliers or light detectors at the end. And the idea is that when the neutrinos from the reactor will travel through the detector, they may hit a proton, and within that process, a neutron will be exit the nucleus, and a positron. The positron, they know that it will decay into two photons, and it will emit light. And again, that's why they put light detectors at the end of the setup. So we can collect that light from the decay of the positron, and in order to see if we still have the neutron, we have to somehow also detect the neutron. And what the clever idea is that we should put some material who can capture neutrons with a high efficiency. So instead of the neutron bouncing around, we should capture the neutron with a given material so that it gets captured promptly, and once it gets captured, it will release some energy, and we can collect the second signal. So basically, the design and the idea is that this interaction will produce two signals. One is going to be prompt. You will see the decay into the positron, a flash of light, and then your neutron, after a few microseconds, will get captured within one of the nucleus in your target. And again, because it will get captured, it will release some energy. And then you can see this as a second signal. So basically, you need for a prompt signal and a delay signal. The idea is pretty simple. You have to have this coincidence based on the average time that the network would capture. What they did is they say, okay, they developed the electronics to measure this coincidence with a given time window, and also they were able to turn on and turn off the reactor to see if the signals disappear or appear, what is the background. Of course, some cases, just from out of the randomness of the process, you will see something that is uncorrelated, but happen to be correlated. That's known as accidental coincidence. They take into that consideration, and they were able to do their measurements. And at the end of the day, they were able to publish the first detection of neutrinos. In the paper, they found that their results were within 5% of the prediction. So when people calculate what is the cross-section, how often these neutrinos from the reactor will interact with the matter, they found that to be within 5%, which is remarkable. And of course, they were gracious enough to write back to Pauli saying, this is a telegraph. I don't know if you ever hear about telegraphs. There was a private form of communication before emails. And they wrote this to Pauli that said, we can tell you that we have detected neutrinos. And after 26 years of postulating this idea, this crazy idea, missing the conference because of the party, people were able to measure, to detect what's supposed to be indetectable. And that was a big leap in terms of particle physics, detecting neutrinos. So now it moves into the 1960s. This is Rice University, this is Rice Stadium, and during that decade, President Kennedy came to Rice and make a big announcement. I don't know if you have familiar with that code. It says, we are going to the moon, not because it's easy, because it's hard. So that's a famous thing that happened here at Rice. And often we at Rice use the same code when we play against UT Austin football. We are doing this not because it's easy, but because it's hard. And you can imagine who always wins. So yeah, that's something that Rice always claimed, quoting Kennedy during the football game. And by in the 60s, people were looking into particle physics and understand more things. We know that there are protons, neutrons. We know that there are neutrinos coming from beta decay. We know that there are electrons. And people were starting to see new particles, something called muon and pions. So the pions, they say they interact with a different force, which is known as the strong force. Neutrinos, yes, they can be described by Fermi theory. And we know that muon decays into different particles. And one of the questions back in those days is, okay, we know that a muon will decay into an electron and an electron neutrino, but also another neutrino. And the question is this neutrino the same as this neutrino, or they are different? So we know that these neutrinos exist from beta decay, but we know that this new particle will also decay into an additional neutrino. Are they the same? So the question was like, if they are the same, we should see something similar to the inverse beta decay. You have an electron produced. But if not the same, if let's say you have something called a muon lepton, and for every lepton you have an associated neutrino, you should see some kind of a muon neutrino, and we can do the same analogy as the inverse beta decay. So one of those neutrinos will escape the decay and will interact with another neutron, and therefore you will produce the corresponding lepton. As opposed to an electron, it will be a muon. So the idea is like, oh, let's see if these neutrinos are the same or different. And people come out with the idea to say, okay, we can produce these neutrinos in a controlled environment, as opposed to decays from nature. So what we can do is we can set protons into a target, produce pions that will decay into muons, and these muons will decay into these neutrinos. So this is the first approach that people use to develop what is known as a neutrino beam. Later today, you will see at the decay talks about how you produce neutrinos. So I don't want to go into the detail. So this experiment happened in 1962 at Brookhaven. This is a national lab in Long Island in New York. And it was led by Lederman, Schwarz, Steinberger, picture here, and just one note, Lederman used to be the Fermilab director, and he used to live on site at Fermilab, and I happened to meet him a few times at Fermilab. He loved horses, he used to have a ranch there, and it was something very cool that I never imagined, that I run into the elevator and I found a Nobel Prize winner at work. So this was when I was a master's student, and I run into a Nobel Prize in the elevator, so we're like, oh, this is super cool. And so I met a Nobel Prize winner at work, basically. So what they did is like, they have to find setup, they have to find a detector where they can measure these things. They use something called a spark chamber, which basically produces sparks. And they say, if we have this interaction, the neutrinos will interact with our detector, they should produce a muon, and by that time they see a muon should look like there's like a straight line. So this is the muon track. As the muon passes through the spark chamber, it will produce these sparks. The opposite, the difference between a muon and an electron is that the electron will produce this kind of a messy, sparkish shower. And you can see by eye clearly distinguish this versus a straight line, right? And when they did that, they found that out of the 113 events, 34 events were single muons that originate inside the detector. They were consistent with these neutrino interactions. If this neutrino is the same as the beta decay, you should see similar number of events, right? They will produce in the same way, in a similar amount. But they found only 6 electron showers. So a new type of neutrino was detected now. So we found that this is a different neutrino and is related to the muon lepton. So now, in the 1960s, we say, okay, the Fermi theory works with the beta decay. We can expand this theory to something more complex and robust. By doing that, they introduce the carriers or bosons. So these particles are the responsible for carrying the interactions in the weak interaction. So one is called the W and the C. One of the features about this is that the Chow range of this interaction is very small. That's why it's called the weak interaction. Because, for instance, electromagnetic, although at the level of the nucleus, the weak interaction is stronger than the electromagnetic force, you can see that the electromagnetic force acts in a long range, right? When you have a spark from your blankets and all of that, it's just because it works on a long range. And you never feel something like that if the weak interaction will be short range, because yeah, you have to be in the micrometer scale. So that's what they did. So we improved beta decay theory, and yeah, still this weak interaction that we will call explain pretty well the beta decay process and the fusion at the sun. How does this weak force works? So basically, we'd say we have this W, we have this particle that will mediate the interaction between the neutrinos and the targets. And what it happens in reality, so the weak force, what is happening is we know that within the proton and the neutron, those are made of fundamental particles called quarks. And what is happening is that one of the quarks changes flavor. So the neutron is made of an up and down, 2 down quarks. So when we have an interaction with a W, one of those quarks changes flavor and becomes an up quark. And therefore, you have a proton. And then you have the electron neutrino and the electron. So that's what is happening. It changes the flavor of the quark. So it's not just the spontaneous transition from one proton to a neutron in a 4-body interaction. It is still a 4-body interaction, but it's mediated by this new particle, what we call W. And what is happening in reality is that this W changes the flavors of the quarks, and you have these products for that interaction. And the same, by that time, people were very interested in the sun, and they know that the core of the sun was mostly just hydrogen. So they know that within the core of the sun, there was a lot of proton-proton collisions. And those proton-proton collisions will produce deuterium, and basically that's the same happening. From out of those protons, one quark will change flavor and become a neutron, and therefore you have deuterium. And again, similar to the beta decay, you will have the corresponding electron and the electron neutrino. So then we say, okay, seems like we are getting our act together. We understand neutrinos now well. We know that they are producing beta decay. we know that there are different kinds of neutrinos. We know that we can explain the interaction of neutrinos through the weak interaction. We have measured neutrinos from beta decay, from reactors, which is the inverse beta decay process. So now, what if we can measure neutrinos from the sun? That's the next challenge, right? And they started doing that. And in the 1960s, two physicists, Rain Davis and John Bacall, started looking at an experiment about measuring neutrinos from the sun. Remember, the core of the sun is mostly hydrogen, so proton-proton collisions will happen a lot there. So what they did is that John Bacall basically do the calculation based on this reaction. How many neutrinos should I expect in a given period of time? So the flux per unit of time, per unit of area. And they say, okay, we should see them. It's not negligible. So they say, now how we can detect those neutrinos? And the basic idea was pretty much the same as was before. So you have the neutrinos that interact with one nuclei, and that nuclei will interact via the weak interaction force. And in this case, one of the neutrons from chloride will become a proton, and then this chloride will become an argon-37, and then the electron, right? So it's basically the equivalent. This reaction will be the equivalent to use a neutrino, hitting a neutron plus giving a proton plus an electron. So now the technical challenge is just, if this interaction happens, we just have to count how many argons is produced in our detector, right? If we count how many argons we have, we can count how many neutrinos are interacting in our detector in a given period of time. The surprise was that only 1/3 or 1/2 of the neutrinos were observed. So something was wrong. Either Bacall calculation of the neutrino flux was wrong, the solar model that was assumed was wrong, proton-proton collision maybe didn't happen at all at the sun, or the setup of the experiment was wrong, there was something wrong, some missing or unknown source of background, or the analysis was wrong, or everything was wrong, right? So we're like, what's going on here? And they tried to do the calculations, and they still see the same issue. There's something missing. We only see some of the neutrinos that we should expect given the solar model. So far, what we found is, and I'm going to try to pause here so we can have a small break and also answer any questions, is that neutrinos were postulated by Pauli in order to solve the beta decay crisis, right? So they were missing energy in that process, and Pauli says there must be a different particle that is carrying the missing energy. You have to have spin 1.5, should be very small in mass, and it should be neutral. So Fermi took that and developed the beta decay theory. But when the beta decay theory was developed, and they do the calculations, how often these neutrinos will interact with matter, they found that they barely interact with matter. So that was a big challenge, whether these neutrinos will be detected at all or not, because they rarely interact with matter. Then the discovery of neutrinos was made through measuring neutrinos from reactors, from the inverse beta decay process. And that was a big success. So we detect what we're supposed to be undetectable. And then people keep working on that, develop the weak interaction theory. And they find out that through this weak interaction theory, there are different types of neutrinos that are associated to the lepton. So we have electron neutrinos, we have muon neutrinos. They are different. The muon neutrino will interact through the weak interaction through a W. It will produce the equivalent lepton, which is in this case a muon. When the electron neutrinos will interact through the W, they will produce an electron. So there was some correlation, and it's when you can see that, okay, we have families of leptons. We have the electron, the muon, and the neutral particle, which has the electron neutrino and the muon neutrino. And everything seems to be making sense, and people were connecting all the dots. So neutrinos are produced at the sun, are produced in beta decay process. We can measure them. We can detect the new kind of neutrinos through the decay process from the muon neutrinos. But then the puzzle was like when we look at neutrinos from the sun, they seem to be disappearing. We don't know, either we don't know how to count neutrinos from the sun, or we are doing something wrong. And this was what is known as the neutrino solar problem. And this was 1960s. So I'm going to pause here, and do you guys have any questions?